Okay. So Andy Pershing, I talked with you guys back on Monday or Tuesday, something like that. I'm excited to come back and talk to you about some of the work that we're doing now at Climate Central around attribution. And this is something that I'm actually hoping to be working on a little bit personally next week during the workshop, and hopefully in collaboration with some of you as well. So very quickly though, last time I talked, I told you a little bit about who I am and my history. I want to tell you just very quickly a little bit about Climate Central. So our motto is science made clear, climate made local. We really exist to bring really great science content out into the world, especially through the media, with the idea that that's going to drive people to make better decisions around climate change. So a little bit about us. Climate Science Research and Communications NGO. We do climate science, we do journalism, and we do communication. We are nonpartisan, we're policy and technology neutral. So we're not going to be, up on Capitol Hill advocating for a particular kind of policy or a particular strategy for solving climate change. We do have a very strong perspective that, CO2 in the atmosphere is bad and that there are impacts that we should avoid. But we're not going to be very prescriptive about exactly how we should go about doing that. A few of our kind of signature programs, our Sea Level Rise program is one of our best known and longest lasting programs. So we have a variety of map tools. So here's one showing the counties in New Jersey and mapping the affordable housing that's at risk from sea level rise in 2015. There's a lot of stuff that we do with sea level rise. Including some really cool stuff, trying to do photorealistic imagery of exactly what the coast of the country will look like with different levels of flooding. We are probably best known, though, for our work with TV meteorologists through our Climate Matters program. So this is an example of a meteorologist from Albany, New York, using one of our graphics showing after kind of an extreme rainfall event in Albany, we provided a graphic that showed, how extreme rainfall is increasing in his part of the world, and so he was able to use that graphic to help connect the experience of his viewers with the big climate change trends. And so before I talk about specifically about our work, I just wanted to tell a little bit of my role at Climate Central. So happy to also, next week talk to people a bit about kind of careers, especially different career opportunities outside, outside of academia, where I imagine most of you have spent most of your adult life. So I'm currently the Vice President for Science, which means that I'm in charge of organizing our science team. So I bring the science team together. I help them figure out, advise them on, different products and content that we're producing, different analyses that we're doing. And that supports our communications mission. So we do the analysis that then goes into our Climate Matters program, or we do the analysis that then goes into our Sea Level Rise program. And I put for now here, and I'll explain that in a second, we're actually in the process of searching for a successor for me as VP for Science. I'm also what's called a director. I'm the director of our Attribution, Science, and Climate Fingerprinting program. And so that means I'm pulling together different capacities across our organization. So not just the science, but also our communication, our engagement, our technology, to try to put together our attribution program, which is meant to try to put out high frequency messages that connect weather, extreme weather with climate change. And so it's both the science and the tech, but also the communication strategy behind that. And so I'm pulling that together as when I have my director hat on. And I also have another hat that I got this summer. I'm the Chief Program Officer, which is why I'm giving up the VP for Science role, or hoping to get somebody really awesome to replace me. And that means that I'm kind of responsible for all of our programmatic work. So basically everything that isn't fundraising and everything that isn't like kind of organizational, like accounting and stuff like that, falls in my domain. So I'm working with our science, tech, engagement, and communications and content teams. And then I'm working across our programs, Attribution, Sea Level Rise, Climate Matters, and our journalism program, to try to pull everything together and make sure that we're achieving our mission, which is to help people see, feel, touch, taste, and smell what climate change looks like in the US and around the world. So I'm now going to shift gears. Now we'll get into the content here. I want to talk about I want to talk about what we mean when we talk about attribution. So I'm going to start with this phrase. So this is what I was taught back at back at Cornell. I don't think Chuck told me this because I think Chuck was actually smarter than this. But I think some of the atmospheric sciences that scientists that we were hanging out with, we're pushing this idea that no single weather event can be linked to climate change. This is in the talking points that a lot of scientists, a lot of meteorologists still have today. But 2004, there was a study that came out about the European heat wave of 2003. This was a deadly heat wave. I think it killed like 15 or 20,000 people. And this study was the first event attribution study. So they went in and diagnosed how climate change increased the odds of that event and how climate change made that event more severe, right? So they were using climate models or using trends to try to diagnose exactly the role that climate change played in making that event more likely and more severe. There's a whole bunch of work that went on heat waves, on major rainfall events, on hurricanes, like Hurricane Harvey was a really important one. And all of that was taking place in the scientific community with graduate students and postdocs doing studies of events, publishing them in the peer-reviewed literature. By 2015, Climate Central helped found an organization called World Weather Attribution. They're now an independent organization led by Freddie Otto in the United Kingdom. They've basically taken the toolkit out of the kind of academic research mode and brought it into more of an operational mode. And so they will go in after a major weather event, and they will do an impact study. They will look at how climate change made that event more likely, or how it made, in some cases, how it made it more severe. And interestingly, they do occasionally do those analyses and actually find that they actually get a negative result, or a null result. They find out that climate change was not a major driver, and in fact, the disaster that they're talking about had more of a human component. And I think those studies are really interesting. And then in 2016, the U.S. National Academies came out with a report that basically put kind of a seal of approval on the methods that World Weather Attribution and others were using, saying that this kind of extreme weather attribution was basically ready for operational use in the way that World Weather Attribution was using them. And so all of this work, right, 20 years of work, and I think now really the media narrative has changed so that climate change is an important factor in many weather events. And it's really, can we quantify it and to what degree? And so it's almost like we've sort of flipped, if you're a Bayesian, we're sort of flipping the prior from assuming that there's no effect of climate change to starting from the prior assumption that there is an effect of climate change. And in some ways, the burden of proof is to say that it's not a factor in sort of weird weather events. Okay, just another reminder, event attribution. We're not going to talk about the cause question, although I will come back to that. At what point can you actually say that climate change caused something? We're going to talk about changes in likelihood, and we're going to talk about changes in magnitude. So the Washington Post example on the lower right was from Kevin Reed at Stony Brook, showing that Hurricane Ian from 2 summers ago, that climate change added 10% to Ian's rainfall. That's a very typical kind of number that you find for hurricanes and other major rain events, that climate change is adding something like 10 to 12% to the amount of rain in those events. Okay, well, what can we attribute? What can we link to climate change? Well, we can really think about this along an axis of things that are hard to attribute and things that are relatively easy to make these attribution statements. And in the latest IPCC report, they actually called out attribution, but really when they were talking about it, they were talking about trends and global patterns. They're not talking about events. Excuse me, but at the trend level, right, the warming trend on the planet, the frequency of heat waves, things like that, the temperature here that on the lower right, very strong attributability. The trends are very clear and very strong. For hurricanes, right, the symbol here in the middle, things are a little bit mixed, right? There are some really great global studies showing that hurricanes are getting stronger. They're more likely to get to category 3, 4, and 5 than they were in the past. They're also extending to higher latitudes. which is an important effect as well. Good evidence that rainfall patterns are changing, that wet areas are getting wetter, dry areas are getting drier. That's an attributable climate trend. And then even things like wildfires, there's good evidence of changes in global patterns of wildfires that you can confidently link back to global warming. But again, it's much harder to do these kind of compound events than it is to do something like heat. But if we talk about events, then we get an even greater separation. And a lot of this has to do with the scale of the processes. Some of it has to do with the availability of data, and some of it has to do with the complexity of the processes. So temperature still remains relatively easy. Temperature data is abundant. Temperature is well behaved statistically. You get like lots of like normal or nearly normal distribution, so the statistics are easy. Whereas precipitation, the statistics are really hard. You have a lot of zeros, you have long tails, so it's harder to do event attribution for precipitation. You can do it, but it's just harder. And then things like wildfires are really tough because you have because they're just complex, because you have different kinds of weather coming together. It has to be warm, it has to be dry, it has to be windy, right? That's what fire weather is. But then you also have something to burn, right? So it can be warm, dry, and windy, but if it's in a desert, you're not going to get a fire, right? Because there's nothing around to burn. And you have to have some sort of an ignition source. And also humans are going to get involved both on the fuel side and on the ignition side. So that can make the attribution complicated as well. But the main point here is that we can divide the world into things that are easily attributable and things that are hard. And I like to do things that are easy. And so this is what we took on at Climate Central, because our goal was really to develop a system that we could use every day, everywhere. We're not going to come in after a particular event, although we can do that. But we wanted to have a global service where we could look any day and be able to say something about the link between that day's temperatures and climate change. And so this is what our service looks like. This is the Climate Shift Index. You can get to it at csi.climatecentral.org. It's a kind of a fun interactive map. And so this is the map from, even though it says today, it was actually yesterday when I got when I pulled the image. So you can see areas where it's warm and areas where it's cool. So this is just temperature anomalies. This is just the daily temperature anomaly relative to the 1991 through 2020 normal. So you can see it's cool on the West Coast where you all are. It's also cool in the East Coast where I am. If you want to feel warm, you go to Texas. If you want to experience locally warm, although it's never actually warm in Quebec, you could go up to Quebec, right? So you can see where things are unusually warm. Now we bring in attribution, and we are able to say that the temperatures in Texas are 5 times more likely in a world with climate change. That's level 5 on our climate shift index scale. Even though the anomalies were higher in Quebec, there's less attributability there. We're at level 3 and 4, so 3 to 4 times more likely. But then we also have these gray areas, like where you all are, where it's actually it's -5. That means that the temperatures that you're experiencing for this time of year are 5 times less likely due to climate change. What you're experiencing is a very rare event in today's climate. Similarly, we're encountering those sorts of temperatures down in Florida. But if you look around the world, you see a lot more red and orange and yellow on the map than you do gray. Okay, so that's air temperature, but we also have done ocean temperature, okay? And that's, and a few of you, I think, got an invite for our launch of our Ocean Climate Shift Index last week. And it looks like this. So again, very similar. Anomalies relative to 1991 through 2020. This is using the NOAA OISST data as the backbone of our work. So you can see, right, it's lots of unusually warm conditions off of the Grand Banks, off of Newfoundland. We got some, in the Central Pacific, generally warm conditions in the Eastern Pacific right now, warm conditions in the Gulf of Mexico, a little kind of interesting blob of blue in the center of the Atlantic. Remember that, we'll come back to it. And then you also can see the wave trains in the equatorial Pacific associated with La Nina. Okay, now we bring in the attribution. So what you see is, first of all, a lot of red on the map. The next thing I want you to see is that our scale has changed. Remember when we were talking about air temperature, we went -5 to 5, and 5 was a really big kind of interesting event. When we've moved into the ocean, we actually have changed our scale. We're going up to essentially level 800 times more likely for the blob in the central Atlantic. And over here in the Pacific, we're looking at conditions that are like, 50, or 10 to 100 times more likely in the Pacific right now. The Gulf of Mexico, this is one of the reasons why we're so worried about hurricanes, right? Conditions there are close to 100 times more likely. One thing I want to do is just to check out the El Nino region or the ENSO region, right? You've got the cool here because we're moving into La Nina, a little bit of warm over Ecuador, right? But notice when we go to the Ocean Climate Shift Index, it's basically white, right? I'll explain why that happens in a minute, but just I wanted to plant that seed. Okay, and the reason that the reason that we see this cool area is because of Hurricane Ernesto. That is the pathway that the hurricane took through the North Atlantic. It pulled heat out of the ocean. It mixed up water from below, cooled the surface temperatures, and so we are seeing unusually cool temperatures because of the storm that rolled through there. And so we developed, because Climate Central, a big part of what we want to do is be able to help people make the link between extreme weather and climate change. We worked on ocean temperatures really because we wanted to bring out that hurricane story. And here it is again. We actually have a paper that is in review right now that actually makes attribution statements of hurricanes based on the ocean temperature attribution. And the top line is that the maximum intensity of hurricanes now is almost always a category higher than what it would be in a world that didn't have an atmosphere chock full of CO2. So we really are seeing an altered ocean environment, and that's leading to big changes in weather. Okay, I just want to show one quick example, and then we'll get into a little bit more science. So this is an example of a meteorologist using the Climate Shift Index last week.
It's time for the Fahrenheit bonus. So if you've been watching me, you know that water temperatures all around the globe have been record high for about the past 12 months, and not just a little bit, by a ton. So what we try to figure out is what's causing this, and part of it is obviously climate change. And so we have a new tool which can tell us just how hot the water is relative to what it should be. And climate change is making the water temperatures in the Gulf of Mexico 400 times more likely, but that's not the hottest spot. Just to the east of Bermuda, we have a spot where water temperatures are made 800 times more likely by climate change. That is
okay. I just want to point out. So Jeff is one of our best, and Chuck, he's a Cornell grad. But I want to point out he got one thing wrong. He doesn't usually get things wrong. This 800x blob we're not talking about temperature. We're talking about the attributability of the temperature. So again, just remember, like, we have places like the equatorial Pacific where you can have a really big anomaly and we get a very muted response in terms of attributability. We also have places, and the central Atlantic is one, the Gulf of Mexico is another, where you don't have to have a really big anomaly to get a really strong level of attributability. Okay. So I want to now talk a little bit about the science. Okay, how do we do this? Well, the challenge that we have when we're doing event attribution is that this is what global warming looks like. This is the global mean temperature going back to 1880, right? So you can see the rise due to global warming. But this is what we have in terms of data. This is air temperature. It's not quite as bad in the ocean, but for air temperature, we have in Denver, you can see just all of the variability that we have to deal with. We have seasonal cycles, right? It's warmer in the summer, cooler in the winter. We also have weather on top of that, right? Heat waves, cold waves, things bouncing around. And so it's really kind of trying to grapple with how global climate change is embedded in the signal that we have over here in terms of the signal of daily weather, or in the ocean, the daily ocean temperatures. So the paper, I believe this is, we've shared this with all of you by Joseph Giguère, who's one of our lead analysts here. He led the study building on methods that Daniel Guilford, who's also at Climate Central, developed a couple of years ago. And so I'm going to walk you through a bit about how we do these calculations, and then I'm going to talk about how some ways that I think we might be able to use them. Okay, so the way that we're going to do these calculations, right? Remember, we're dealing with both the global climate change, right? The global mean temperature, and we're dealing with variability, daily weather scale variability. So the first thing we have to do is to characterize that daily weather scale variability. So here, what we're going to do is we're going to look at over our reference period, so 1991 through 2020, a standard reference period. We're going to look for the day of the year. And we actually use a 1 month window centered on the day that we're centered on the days that we care about. So we're going to characterize what's the variability in temperature at that location, okay, for that time of year. And so we'll get something that looks kind of like a normal distribution. We actually are fitting what's called a skewed normal distribution, which is a normal distribution with an extra parameter that allows you to kind of tilt it, which comes up in some places from time to time. Okay, so we have our distribution here. This represents the world as it was for our reference period, which the mean global mean temperature over our reference period, again, 1991 through 2020, was 0.8 degrees Celsius above the pre-industrial. So now what we have to do is what we're going to try to do is transform this distribution to simulate both the current state of the climate and then a climate without global warming, what we call the counterfactual climate. So the first thing we're going to do is look at that location for that season, and we're going to do a regression between the local temperature and the global mean temperature. And what we're interested in is how sensitive that location is at that time of year to a change in global mean temperature, and we call that parameter beta. So there's some places where beta is going to be less than 1, and so those are places that are not going to warm up as much as places where the beta might be greater than 1, where those are going to be more sensitive to changes in global temperature, so that we would expect them to warm up more. Once we have that parameter beta, we can basically multiply it by the change in global mean temperature to shift our distributions. Okay, so we can create a distribution for today's climate of 1.3 degrees Celsius by taking beta times 1.3 minus 0.8. Okay, and that's going to nudge that distribution up. We are going to nudge it down by taking beta times 0 minus 0.8, right? We're going to cool it by 0.8 degrees back to a hypothetical counterfactual temperature of 0 degrees. Okay, so now we've taken our distribution, we've split it into 2 distributions, one representing our modern climate and one representing this counterfactual climate. And then what we do is we take our observed temperature T down here, and we look at the likelihood, the probability density function value for the modern climate, that we're going to call that P modern. We get it for the counterfactual climate. We're going to call that P counter. We're going to take the ratio of those, and we're going to apply a log. Okay, so we're going to take the log of the ratio. Now, what I've described here is what we call our median method. And that means that we fit beta to the median of the distribution. And so that assumes that whatever the shape of the distribution is, we're just smoothly shifting it, basically just shifting the mean or the median around. We also have another method. We call it the quantile method, where we fit a beta for 21 different quantiles. So think about the first 1%, 2%, 3%, et cetera, all the way up to 99%. And then what that does is we get a beta for each of those quantiles, and that allows this distribution to warp and bend as we do this transformation to the counterfactual and to the modern. And so that one assumes that the climate change may act differently on different sides of the distribution. Then we also bring in climate models. And I really love the climate models because the counterfactual is much more direct, right? The advantage of the empirical methods is that we can do it based on data, and everybody loves data. We can do it based on data and that gives us a very high resolution view because we have really great data for the atmosphere and the ocean and much finer resolution than we get from the climate models. The climate models, you give up the resolution, the spatial resolution, you give up some of the process realism, but you get this just really direct measure of the influence of CO2 on these distributions. And so here we take the forced runs, which are the runs using the historical CO2 forcing, and then extended out with any of the SSP scenarios. And then we will look up where in that forced run for each of our 24 models, when does it cross our 1.3 degree of warming? And that gives us our pink distribution, our modern distribution. We also have control runs. Control runs are essentially initialized and then they just let them fly, and we don't add extra CO2 from humans into those control runs. And so that gives us a counterfactual of our no global warming counterfactual. And so then we'll compute this log of the ratio. The reason we compute the log of the ratio is that we can then add and average these things together. So we're going to take an average of our two empirical methods. We're going to take an average of our 24 models. We're then going to average the two averages together, and then that's what we represent with the climate shift index either on the land or in the ocean. Okay, so there's a lot going on here, but the logic here is that we're trying to account for is that what we've done is we've set up a system so you can kind of look at what are the places where where the system is going to be sensitive, that's going to change the values here. So one is like if T, for example, moves out towards the tail, you're generally going to get a bigger response. We're going to get a bigger ratio as T shifts away from the middle. So when T's in the middle, P modern and P counter are going to be equal. So log of 1 is 0. And so that's the center of our scale. All right. The more we shift our distribution, so the stronger beta is, the bigger change we're going to get. So that's going to give us our high values if we have a large beta. And so what that means is for places and times of year where we've observed a lot of warming, we will generally get higher values. So that's going to be, and for places where we have less warming, we're not going to, those distributions are going to be closer together. And so we're going to get lower climate shift index values or lower ratios. But that is essentially fighting against variability, right? So if the variability is really large, these distributions are going to overlap more. And so that's going to depress the values and bring them in towards 0. And so that's the sort of thing that we're fighting with. Okay, and I'm going to call this thing log of the ratios. I'm going to call it the change in information due to perspective, or CHIP. It's just the name that we've been using internally to talk about this, and you'll see that in Joseph's paper. So I'm going to use Joseph's paper to show you some of the features of this kind of attribution stuff, and the paper's published, so the results are not preliminary. Please cite and distribute. So this is what the temperature anomaly looked like in July for 2023, right? So last year we were in the middle of an El Nino, so it was warm in the Pacific, in the equatorial Pacific. We also have this kind of cool warm band in the eastern Pacific, and the Atlantic is generally really warm. And we have again more of that warm blob off of Newfoundland. So then we add in CHIP. And so this is a different scale than what we show on our tool. This is that CHIP metric. So it's very much like the straight product that we're going to use for more of a research application. And so just to see how this attribution works, for one, oh, by the way, we can sort of average CHIP up, and we can say that the average location in the ocean has a CHIP of 2.4, which is, I believe that's on average about 6 times more likely. Okay, so if we zoom in on this area, right, this band in the western or in the eastern Pacific, you can see like the warm area maps to a high CHIP, right, red. The cool area maps to a negative CHIP, which is temperatures that are less likely in a warming world. You encounter those temperatures less often in a world with that's been forced by climate change. If you look at the tropical Pacific, you see that while we have a really, really strong anomaly, we have very muted chip values. And that's because of essentially what's happening there is while there has been warming in the Pacific, right? La Niñas now are warmer than La Niñas were in the past, and El Niños now are warmer than El Niños in the past. But the variability in that region is so high that it tends to depress the chip values in that location. And so you really see that in the map for if you go and look today, where it's basically white in that region. And then we also have places, right, where you can have really small anomalies leading to really big chip values. And these are places where you have generally lower day-to-day variability, right? The Gulf of Mexico, it's basically always hot in the Gulf of Mexico, and sometimes it's just extraordinarily hot. So it's we have very low variability in that region, and the climate changes and the climate trend is strong. The warming trend is strong, and we get a lot of support from the climate models that warming, that we should expect warming in that region, and so we get a stronger response there. Okay. We can also do this to diagnose a particular heat wave. So this is the Gulf of Maine 2012 heat wave. This was in Joseph's paper. So the red is the sea surface temperature averaged over the Gulf of Maine. So you can see that we had our highest anomaly in June of that year, which is when the lobster fishery went crazy, what I talked about earlier in the week. And then we have generally positive anomalies throughout the year. Most of the year was above 1.5, and occasionally we got up to, when we're averaging over the whole Gulf of Maine, up to 3.5 degrees Celsius above normal. Now, the chip value, right, which is giving us our level of attributability, that is blue. And so early in the year, we are around 2. So a chip of 2, it translates into, should be able to do this in my head, I believe it's 4, right? 4 times more likely. But we actually get up to a chip of 4 later in the year. And so again, what we're seeing a little bit is this kind of interplay between variability and between the trend. So we have much more confidence that warming in the later part in the fall in the Gulf of Maine is a feature of climate change than we do warming in the spring. In the spring, we just have a lot of variability in the Gulf of Maine. In the fall, we've had a lot of observed warming, and that's supported by the climate models. So we get a stronger level of attributability for the same level of temperature anomaly later in the year. And then you can look at, we can begin to look at the map in space. So here's the temperature anomaly. So you can see there were kind of 3 or 4 blobs of even more extreme anomalies. This is on the day of maximum chip. And then the chip starts to, break that apart and assigns it a little bit. We get kind of a stronger response here in the eastern Gulf of Maine, which has generally lower variability than the western Gulf of Maine, which has higher variability because of the weather coming off of the continent. Oh, and I should point out this parameter over here, scale factor, this is beta, right? This is that local sensitivity. So you can see we have more sensitivity in the eastern Gulf of Maine, very high sensitivity off of what's called the Northeast Channel over here. And we have lower sensitivity off of Georges Bank. Okay, so what I did was I walked you through how we do these calculations around the likelihood ratios. The likelihood ratios are really great because they're really great as a communication tool, because they give us a lot of variability. They give us a lot of changes across space. They give us a lot of changes day to day, which works really well for the communication goals that Climate Central has. So we're able to talk about climate change and how climate-y an event is on a particular day anywhere in the world. But for a research perspective, that's not always what we want, right? Likelihood ratios, they're just a likelihood ratio, right? Nobody, if you were, I guess, betting money, it would be, it would be a useful thing to have. But for most of the things that we're going to be interested in, which are going to be things like impacts in the ocean, we actually want temperature, right? And so what we can do is use our same machinery and actually pull out what we call the counterfactual temperature. So the way we do this is we take the observed temperature. So rather than looking at the probability density functions, we look at now a cumulative distribution function associated with the same distribution. We take today's temperature, we look up what the quantile associated with that temperature. We then find the quantile associated with that temperature in our counterfactual distribution, and then we get the temperature that would give us that would occur with that same probability in the past. So you're assuming that sort of the probability is sort of stochastic, and then we're looking at where we're looking at kind of the shift in the mean, and that gives us our counterfactual temperature. If you average the counterfactual, if you take the difference between the temperature and the counterfactual temperature, we call that the intensity. If you average the intensity over planet Earth over the year, you're going to get 1.3 degrees C. And in most of the time, this counterfactual temperature or the intensity doesn't change a lot day to day at a location. I mean, it will change somewhat seasonally, as we kind of saw in that Gulf of Maine example. But for the most part, it's going to be fairly stable, and it's going to be something close to this 1.3 degrees, give or take, depending on where you are in the world. But I think this is a really useful tool. And this is one of the things I'm really interested in starting to do some work on, perhaps next week. So the way I think we can use this tool, and the way we're starting to use the counterfactual temperatures at Climate Central, is to do things like this. So imagine that we have our observed temperature, our modern distribution. So it's a little cool, a little warm, a little cool, right? Now, suppose we have a model, right? We have some process that we know is related to temperature. Okay, that process, maybe it's fishery recruitment, or maybe it's the location of a species, or maybe it's maybe it's the strength of a hurricane, right? Something that that we can say is a function of temperature. So if we have that model, we can then model the process using our modern observed temperatures. And so here I'm using essentially a running mean kind of process. So it goes up. It generally goes up, goes down a little bit, goes up. Okay, so that we have a temperature, we have a model, and we have a process. Now we can take our counterfactual temperatures, and let's say it was, we have a little bit of cooling here, and then we have a big jump, later, maybe later in the year. We then run those counterfactual temperatures through the model, and we might get something like this, which would be a very different view of the process. And this difference is the attributable change in the process due to climate change, right? Climate change if we didn't have climate change, this is what we would have gotten. This is what we got. And so this is the level of attributability. This is what we can say climate change added to that process. So I'm going to show you a quick example. I presented this at Ocean Sciences, and it's something I'm really eager to follow up on. And I'm going to apply this to coral bleaching, so hopefully very relevant to what you're going to be hearing about today. So the model for coral bleaching, this is the model that the Coral Reef Watch developed, is a degree heating weeks model. Again, very similar to this. We're going to add things up over several weeks, and that's our degree heating weeks. And they're going to define it relative to a local maximum monthly temperature. So you look at that location, where is the maximum temperature that you expect to occur during the year, the maximum climatological monthly temperature. So, most places in the Northern Hemisphere, that's going to occur, say, in August, right? So it might be the August mean temperature for the reference period. And then we'll take a 12-week mean of that. So a degree heating weeks, what we're going to do is we're going to take the temperature minus this local monthly maximum temperature. If it's negative, right, if we're below that temperature, we just set it to 0. If it's above that maximum monthly temperature, we add it into our pool, and we're going to accumulate that tally up over 12 weeks. This is what the degree heating weeks looked like last year on October 15th. So for the 12-week period ending on October 15th, you can see that most of these places, many places in the Caribbean, were getting close to basically 12 degree, more than 12 degree heating weeks. And so you're really seeing a big influence of that warm water that we had in the Caribbean last year. we can then say, well, what's the counterfactual degree heating weeks, right? I take our counterfactual temperatures and I drive them through the degree heating weeks model. You can see that most places we actually, without global warming, we would essentially have no degree heating weeks, right? We would have no risk of coral bleaching in the counterfactual world, right? Except for, I don't know, a little bit off of Cuba, a little bit in the Eastern Gulf of Mexico. And so then we can look at the attributable change in degree heating weeks, just taking the difference between these. You can see that we've got, up to 12 weeks. We're getting up to 12 weeks, which is essentially the maximum. And so we're seeing just lots and lots of attributable change in the ocean and translating that into a metric that should be relevant to coral. So here's, if you just average that up for every day across the Caribbean over 2022 and 2023, first of all, you see that 2022 was warm, and there was a little bit of bleaching in 2022, but then 2023 is when the bleaching really kicked in, and you can see that spike that we were looking at in October. So the average degree heating weeks for the Caribbean was pushing close to 10 degree heating weeks in October. Excuse me. So now what we'll do is we'll add in the risk levels according to Coral Reef Watch. So risk of possible bleaching is down here. Risk of reef-wide bleaching is here. Risk of mortality is up here. And so we're seeing a lot of places in the Caribbean that we're getting into this risk of mortality level. I have to say I have not kept up. I don't know what exactly transpired, but I do know that there was quite a bit of reports of bleaching last year. Now, what we'll do is let's look at let's replay the last 2 years without global climate change, and you get a line that you can barely see, right? In 2022, there would have been no risk of bleaching. In 2023, there would have been maybe a little hint of bleaching, or a few corals that sort of woke up and were like, yeah, it's a little warm. I'm not super happy, but nothing compared to what we have. And the conclusion here is really that coral bleaching is essentially getting very close to being 100% attributable, especially these mass bleaching events. They just really would not occur in a planet that wasn't polluted with carbon dioxide. Okay. So that's, I'm going to wrap things up here. So just a few links. If you want to look at today's climate shift index on land, our air temperature climate shift index, that's csi.climatecentral.org. We are not making these publicly available, but we do have them and have started to distribute them to folks who are interested in doing research. We have a 1970 through present hindcast that includes the likelihoods and the counterfactual temperatures. We also have the same thing for CSI Ocean, except it only goes back to 1982, which is when the OISST product started. We are using our attribution tools to produce alerts. So unlike the world weather attribution things that I highlighted where they go in after an event, we're actually trying to say something before an event and say, hey, this event is coming, and there's a climate fingerprint on that event. And so we do that in our alerts, and we also do some retrospective reports there. And then I would encourage you, if you really want to keep up with what goes on at Climate Central, if you want to learn about climate change, especially climate change in the US, sign up for our Climate Matters program. It's free. You'll get a weekly newsletter with interesting graphics that can help you talk about climate change. And now I'm going to stop the share so that I can actually see people.
Great. Thank you, Andy. I think there's a few questions. Erica, you had one?
Yeah, I'm gonna unmute.
Mm-hmm.
Hi. No feedback. Is that better? Can you hear me?
I can hear a lot of you.
Okay, great. I think it's working now. I was wondering if you could perhaps step through your 1 through 7 attribution model, and really I was able to follow pretty much all of it. It was very clear, except for step 2, where you got that beta parameter.
Sure. So the beta parameter, the one way, it's basically a regression between temperature, or the observed temperature at a location, and global mean temperature. So it's not quite a trend, right? Because that would be the regression between temperature and time, but it's a relationship between temperature and global mean temperature. And so what we're trying to derive here is for, if we get a 1 degree change in global temperature, right? If the global temperature goes up by 1 degree, how much warming would we expect at that location? So it's almost like a local climate sensitivity.
Okay, so it is a slope.
It is, yeah. It's the slope of that regression. Yep. And I got your email about the CPR data. I'll try to get back to you today. If not, we'll talk about it on Monday.
Thank you.
Continue with Erica's question. So I wondered, so you do the correlation between the local temperature time series as well with the global mean temperature series. And I wonder whether you do the sensitivity test, like the confidence level, because in some places there has more turbulent signals, the correlation may not be so confident.
Yeah, thank you. So we do, we have worked out kind of the full set of error statistics around around that chip metric. And so one kind of error is exactly what you said. It's essentially the R squared. It comes from the R squared on that regression. And so if we have a high R squared or a low R squared, right, low confidence in the regression, we're going to have a wider confidence interval. And then we also get another estimate of confidence interval from the variation among the 24 models. And we bring those together to make a kind of a single estimate for the error of for a single measure of the confidence that we have in that combined chip metric. And most places it's about half a chip. So it tends to, we have designed in our public facing tools, we basically have set the width of the buckets much bigger than the sensitivity of than the error in the tools, so that we can confidently just give people a number and not always have to report the errors. But we do have the error statistics that we can calculate.
Thank you. And as a second question is, so you give a probability distribution, a PDF, and you give a shape. It means with the worm and without worm, the probability distribution, your assumption is keep the same. But in reality, it should not be the same, because the Oliver's result for the marine heat waves they have tested, they will be rather.
So yeah, great. So remember, we actually have two empirical pathways. So the one that I diagrammed out was the simple one where you're right, you're in that we're assuming that the shape of the distribution doesn't change, just the position. So we just warm it or cool it. We have another pathway where we are trying to get at your question, which is not only just how much does the mean shift, but how do we get any change in the shape of the distribution? Do we get any flattening? Do we get any shift in the variance? And so that's our quantile method. So we actually have that estimate as well. And we kind of like to keep both of them in the mix, because for the quantile methods, we're getting kind of more error because you have fewer samples, right? You have fewer that you have less confidence in the time series at the tails of the distribution. But getting back to your question about, kind of marine heat waves, a lot of the studies that I've seen, a lot of the climate models, like some of the work by Mike Alexander, really kind of are emphasizing that in the ocean, we're not actually seeing a lot of changes in the variability, especially if you account for global warming. You tend to see things staying mostly normally distributed. They're not seeing a lot of tails. At least that's what they get from some of the large ensembles.
Okay, thank you.
Yeah, I don't know if I should turn my volume.
Yeah, good.
Okay, okay, cool. I just don't want to echo. Okay, cool. Yes, thanks for your talk. So there's a number of us who were looking at doing some sort of depth-based marine heat, like depth-based depth-based marine heat wave kind of work, but also looking at if certain heat waves are atmospheric versus more oceanic driven. But I think it would be really interesting if we could also attribute certain heat waves to, you know, climate change, or if there's, you know, what, like seeing that kind of signal with the degree heating weeks. I thought that was super cool. But I was wondering, is that data or that code that you guys did to create those plots, is it readily available or is it private within Climate Central?
It's a good question. It is private, mostly because we just haven't had the time to actually clean it up to share it in a way that's public. So the intention is not to keep it private, but the intention is to release it in a way that where it could actually be useful. So I'm happy to help you show you a bit of how we do it, and we can do that next week.
Hi. My question was rather simple, and hopefully, I'm sorry if I missed this earlier, but the last part of your talk when you were talking or showing those last plots, I was wondering if you could specify again, like what degree heating weeks specifically referred to. Like, was that with respect to a certain threshold and how many weeks it went over that temperature threshold, or was it something different?
Yeah, it's so it's actually, I mean, Mark should answer the question. It's his stuff. We basically just tried to take what the description from the from Coral Reef Watch. But it's basically like you take the temperature, subtract that maximum monthly temperature, so that gives you units of degrees, and then you add them up, and I think you divide by 7 so that you're getting it in terms of degree heating weeks as opposed to degree heating days, and then that's what that metric is. So it's just basically like a running sum, where you've sort of subtracted off that kind of bleaching threshold temperature. Yeah.
Well described, Andy.
Hey, Mark, good to see you again.
Good to see you. Yeah, we'll actually be talking about that a good bit in my talks that are coming up next. So you'll get to hear in great detail. A question for you. So on this new stuff, I was excited to see that example. Is this stuff that you're doing with Derek and Gong and folks at Coral Reef Watch, actively working with them?
I think I talked to them at Ocean Sciences, but it's not so far it's just been kind of me and my computer.
Okay.
Yeah.
Yeah, no, it'd be cool to collaborate on that. I've been thinking about doing this for a long time, and hadn't reached out to folks before I left Coral Reef Watch, and didn't know if you were actively working with them. But this is absolutely something that we've wanted to see tested for a while. So it's really cool.
Thanks. And I think the really interesting thing in the ocean, and you get a little flavor of this in Joseph Jaguar's paper, is that in some ways the no global warming counterfactual is just a little bit absurd, right? Everything in the ocean is so strongly attributable. So we're actually thinking about developing a specific coral counterfactual that would be basically the mean, like represent kind of reference everything to the mean climate of I forget what year you all used when you were kind of defining the kind of the thermal, like the basic thermal limits, but it would end up being something close to 1990, right, as like a reference climate. And the really interesting thing about that is like that's sort of, it's specific to coral in terms of the way you all defined the, you know, the references, but it's also a really interesting kind of human counterfactual, because 1990 was basically about the year where, like, you know, James Hansen said, you know, it's real. Like that's kind of where the scientific consensus emerged. And so warming after 1990 is basically due to our willing stupidity, where before it was just due to ignorance. Yeah, way.
Hey Andy, can you hear me?
Yep.
All right. Nice talk, and I do like the way how you convey science. And also I have a, you know, I still remember last time you gave a talk on the simple model, using simple models to get very interesting results. I mean, science is to make things simple, right? To make the audience, the general audience can understand it. So, you know, I got a question about how to convey these results. I mean, as a climate scientist, we got very complicated maps and data, right? But how can we make things simple? Because I'm also running a climate tech startup with some of my friends, and all of us are like scientists, data scientists, the climate scientists, but we don't know how to make things or convey this our research or make things simple. And I think that's my first question. My second question will be very simple, just something about data. The on the last slide you show the CSI map, you show the hindcast. I'm curious about, can you know, share with us more details about this data? Thank you.
Sure. So I'll take the data question first, and then I'll do the SciComm question next. So for the data question, I'm actually going to be bringing the Ocean CSI hindcast with me, and so it sounds like you're remote, so we'll figure something out. It's large, but it's not super large. So I think it would be great if you had an interest that we could scope it specifically in terms of geography and time and space. But the data consists of, right now, the native format is a ZAR format, which is it's a kind of a cloud-based, essentially like a cloud optimized netcdf file. It's easy to work with in Python and Xarray, but it's a little harder in R. We can easily convert it to a netcdf file. And so in the netcdf file, the variables that we have are the temperature, which is just OASST, the temperature anomaly, just based OASST minus the climatology. We have this thing we call the climate factor. It's basically that chip metric, or the kind of the log of the ratio. And then we have the counterfactual temperature and the counterfactual intensity. And so that's the core data set that we have. And we internally have a lot more in terms of, like, you know, gives us performance metrics around the different models and the different techniques, but that just ends up being a lot, and it's confusing. So I think right now we're planning to just share kind of the core products. So in terms of in terms of science communication, you know, there's no one answer, right? It depends on what you're communicating, but even more, it depends on the audience and what you want your audience to know. And so that's one of the things I've really learned from working with our communication specialists, is that, you know, to really like think about, like, what is it that the audience is going to get and you want them to get out of your work, and really try to drive at that. I think as scientists, we love the complexity of the stuff that we do, and we kind of want everybody to understand it, right? Because we got to the point of understanding through like this process, and that, you know, this sort of the scaffolding of the results and the data and everything kind of coming together. Most people don't need that. Most people just want to know, like, what is it and why does it matter to them? So, you know, a big part of what we've tried to communicate with, you know, with things like the climate shift index is, it's hot, and it's climate change. That's what we want people to take from it. And so, we're really trying to make it as simple as possible, to make it easy for I showed the example of our, Jeff Baradelli, our TV meteorologist, like, he explained it in, what was that, 30 seconds? And that's about 6 times longer than he usually gets, that he would usually get to explain something. Most of the time, especially like these TV meteorologists are explaining stuff 5-10 seconds. And so it just really has to like snap into place for people. And so that's a big part of what we've had to think through.
Thank you.
Erica, did you want to ask your question?
Turning volume, unmuting. Hi again. So I'm wondering if the 1.3 degrees C or the 1.3 number in your step 3 of the attribution model is empirically derived, or if this is like plug and chug from the current anthropogenic warming signal that we
So what it's empirically derived. So we're taking we use the Hadley Had Crew global mean temperature series, and what we do is there was a lot of reporting right last year, and I forget, like, we breached 1.5 for like 1 month or something like that, right? We are trying to filter that out, right? Those sorts of swings, right? There is variability in global mean temperature from things like whether you're in El Nino or La Nina state, right? That's going to push things around. You can have other kind of rando events that are kind of causing global temperature to vary. What we really wanted to do, we define the global mean temperature as the centered 15-year mean, okay, of the global mean. So we're going to smooth, and so that smooths out a lot of those bumps and wiggles. The challenge, though, is that we want to be able to say, well, what's this year's temperature? And we can't do that. We can't tell you 2024's temperature until we get to like 2031, right? That's when we'll have that 15-year record. So what we did was we figured out that actually you can take a 30-year series and fit the trend line, and then extrapolate out 1 year, and that gives you that actually does a really good job approximating that 15-year running mean. And so that 1.3 degree number is essentially like the trend over the last 30 years projected 1 year into the future.
Thank you. Yeah, I had also seen that headline that we've passed 1.5. So that was actually part of my confusion. Thanks for addressing that. I typed up what you said. I'm gonna put it in the chat just to see if I kind of got it, but I know there will be other questions. Thank you.